Good morning. It's time to do the good old morning stream again. I didn't think I was going to be able to. Oop, we've got audio there. I didn't think I was going to be able to make it this morning because last night we had the Node.js meetup, and we were talking to Miles, who was talking about the loaders, the module loaders in Node. I have that on my YouTube channel right now, and it's also it was streamed here on Twitch. So if that's something that's interesting to you, I highly recommend checking that out. Let's see. So pop out chat here. Pop you to the left. However, to this morning, we're going to continue on with Rust. So let's take a look at where we are. So in our Learning Rust repository, looks like we're on chapter 10, thinking in terms of lifetimes. Let's go. Yeah, so it looks like we got about halfway through this sort of section, this subchapter. So what I want to do is open up the terminal and get ourselves set up back in like our code in Rustland. So all right, so here we are in lifetimes. Can open this in code also. This is where we left off, where we were playing around with lifetimes and setting up like the longest string and having to use a lifetime because we have a block here, which in which this string here doesn't live, nor does this result. They don't live as long as this string. And from what I can tell, and I may be wrong with this, from what I can tell, that causes this function doesn't really know, because it's calculating based upon times, like just number values, because the borrower is saying like, hey, this will last for x, x time. This will last for x time. They're not the same, so there's a problem there. At least that's what I understand it to be. I could be wrong. I found somebody else yesterday who knows about Rust and asked them, hey, how well do you know lifetimes? And he just sort of laughed and said, still learning them. So I get the feeling that that's gonna be how I'm gonna do it too. Is I'm gonna be continuing to learn this for quite a bit of time. All right, so let's move on and actually get started with the book here. So, thinking in terms of lifetimes. The way in which you need to specify lifetime parameters depends upon what your function is doing. For example, if we change the implementation of the longest function to always return the first parameter rather than the longest string slice, we wouldn't need to specify a lifetime on the y parameter. The following code will compile. If we change the implementation of the longest function to always return the first parameter rather than the longest, we wouldn't need to specify a lifetime. Okay, so well, it's interesting because they're still specifying a lifetime here. They're just not specifying a lifetime on the second one. In this example, we've specified a lifetime parameter a for the parameter x and the return type, but not for the parameter y, because the lifetime of y does not have any relationship with the lifetime of x or the return value. When returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. Okay, so when returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. One of the parameters? Or any of the possible parameters? I would guess like maybe that's what it is. So if we take a look, okay, so I need to make you brighter. Okay, so if we take, we're saying lifetime parameter of a. So we're initializing a as the lifetime parameter here. String 1, which is created in the main block, it gets a lifetime parameter of a. String 2, which is created in this block, since therefore has a different lifetime, is also being given a here. And result, so that the return, we're also saying a. So which is interesting because result is also going to live just as long as this one. But string 1 will live a little bit longer. So is it because these will live not as long as each other, and so string 1 and string 2 do not live as long as each other does. The return lives only as long as string 2. So because they don't live as long as each other, and from what we just read, if we return a reference, the whatever is returned has to live as long as whichever of these strings we're essentially returning the slice of. That tells me that by doing this, we're then saying, hey, only allow this function to really work if this works, if they can all be given the same lifetime. Stacking, I guess you didn't party hard enough last night. Nope. I was home by 9 o'clock last night. We finished up and packed up, cleaned up the entire place, and I was back home at 9. So it was still a lot of fun. But okay, so I think that's my new theory, is that this is sort of like a filter where it's saying, hey, don't allow certain things in. Like only allow this function to run if this is true, like that string 1 can live at least as long as string 2. That's my thought, but I'm still very new on this. Do you happen to know if that guy ever posted them blog post on a lifetime checker? I was really looking forward to that yesterday. Oh, the person that I asked, his response was, I don't really know lifetimes that well. I recommend just programming and you'll learn it over time. So no, he has not made a blog post. And the other thing is that Mozilla has a office in the building that I work in, and I walked up there, and absolutely none of them are. Someone in chat said they would link to blog post yesterday. Oh, they did say that. Did they? I wonder if they sent me the chat and I didn't note it. Like I didn't notice or grab it. What I could do is I could rewatch the I could rewatch my video from yesterday because it keeps the chat, and we could just like quickly look through. I don't remember it being. I don't remember. I remember them saying like, "I will do this." So maybe it'll be in a future time. But I could check. I can check also and see if I can find it. Okay, so in this example, we specify. Okay, so got this. Consider this attempted implementation of the longest function that will not compile. So we have function longest, we registered lifetime A, X is just a string, Y is just a string, and then we have the lifetime of A, a string. But because X and Y have different lifetimes, we need to tell it which one, I bet. Here, even though we specified a lifetime parameter A for the return type, this implementation will fail to compile because the return value lifetime is not related to the lifetime of the parameters at all. Here's the error message we get. The result does not live long enough. Borrowed value must be valid for the lifetime A as defined in function body. The problem is that result goes out of scope and gets cleaned up at the end of the longest function. We're also trying to return a reference to result from the function. There is no way we could specify lifetime parameters that would change the dangling reference, and Rust won't let us create a dangling reference. In this case, the best fix would be to return an owned data type rather than a reference, so the calling function is then responsible for cleaning up the value. Ultimately, lifetime syntax is about connecting the lifetimes of various parameters and return values of functions. Once they're connected, Rust has enough information to allow memory-safe operations and disallow operations that would create dangling pointers or otherwise violate memory safety. Okay, lifetime annotations in struct definitions. So far, we've only defined structs to hold owned types. It's possible for structs to hold references, but in that case, we would need to add a lifetime annotation on every reference in the structs definition. Listing 1025 has a struct name important excerpt that holds a string slice. So struct important excerpt, we register a lifetime, and then we say, okay, so the part of this important excerpt has the lifetime A, the string, function main, let novel, so we create a string on a heap. First sentence equals novel.split. So we're splitting on the dot. Then we're going through the first iteration. So expect could not find a dot. Let I equals important excerpt. First sentence. Okay. This struct has one field, part, that holds a string slice, which is a reference. As with generic data types, we declare the name of the generic lifetime parameter inside angle brackets after the name of the struct, so we can use the lifetime parameter in the body of the struct definition. This annotation means an instance of important excerpt cannot outlive the reference it holds in its part field. The main function here creates an instance of the important excerpt struct that holds a reference to the first sentence of the string owned by the variable novel. The data in novel exists before the important excerpt instance is created. In addition, novel doesn't go out of scope until after the important excerpt goes out of scope. So the reference in the important excerpt instance is valid. So the data in novel exists. So I want to try this without, because we're just putting in first sentence, but because of this, we're just getting a slice of this, so it's a reference. So I want to try implementing that too. So in our struct, what do they call this? This is important excerpt. and we have a part that's going to be a reference to string. Missing lifetime specifier. So it won't let me do this at all. But if we go ahead and do the rest of this right here, so we're gonna have that sentence equals string from this is the first part. This is second. So then we want to split this. So let first part equals, and we're going to sentence dot split on dot. And so then we're going to be able to call next on this. But we can expect Pack, I assume I missed the answer to my question. Your question was, did someone in chat say they would link to a blog post yesterday? Yes. I don't remember one being linked. I will check it. I'll check the stream, the chat log. But otherwise, we'll have to wait. Dot next, dot expect. And here's where we could just say, could not find this. And then we have let excerpt equals important excerpt part, and this is going to be first part. So yeah, just creating this on its own, everything works. Like we're passing in a reference, we're passing in the string slice, but it's not able to go into here because this is a reference, and so Rust just doesn't know how to deal with that. What we need to do is register a lifetime, which we're going to see if these are local, because we're using the same lifetime here, which is A. And I'm going to try A right here and just see if it accepts this. And we're going to use A right there. If I hit save, field is never used, part and excerpt is never used. So this works then. So we can now print line and say the excerpt is and we can put excerpt, it's dot part, right? So now this should work. Excerpt is, this is the first part. So yeah, that's interesting. So if I, in my struct, if I want to be able to hold references instead of like giving ownership to the structure, then I need to use a lifetime, which can get a little bit annoying. I can definitely see that. It might be a little bit faster because I don't have to do quite as many memory changes, but at the same time, I can also see that it's a lot more annoying and hard to read, and just sort of adds complexity if I need to put in something else, if I need to use these. Also, like the next thing that's really interesting is that what happens if I put, let's see, the excerpt equals important So if I do up here, I'm wondering, is a lifetime just a copy at the end of the day? I don't think a lifetime is a copy. I think it's like a measurement of how long it lives. If I do let excerpt, and then inside of here, I put a block. So if we do this, cannot find excerpt in his scope. It's right here. Maybe I have to do. Oh, interesting. So even if I'm defining, like declaring it out here, it doesn't want me to. I can't use this. Interesting. So if I were to do let mutable, there we go. So let mutable excerpt, that's a misspelling error. Did I? Oh, it is. Haha. Excerpt. Sentence does not live long enough. Borrowed value does not live long enough. So even though I'm using the lifetimes are not like gonna cause it to live any longer at all. Instead, what it's doing is like telling the compiler, hey, I have this extra knowledge that you don't have. You're freaking out, but I'm gonna override you and tell you this is okay. Don't fail because of this. But if I do that, now I still have to worry about these other things here. So sentence is dropped here while still borrowed because I grab excerpt stuff right here, but sentence is removed right here. So the lifetimes are really just because like without these blocks, if I remove these, everything is fine. Everything is fine. It should be fine. I mean, the comments should actually make the block not exist anymore, right? Let's run it again. On line 25. Interesting. So now it's right here that sentence is dropped. But if I remove these, it seemed to have worked before. This excerpt should be gone. Sentence should be gone. Excerpt should be gone at the end of this block. Everything should be gone. Let's try unindenting. I could swear we got it to run. Okay, so the key difference here is excerpt. Okay, so if I take this out, let excerpt, and we create excerpt here, then it works. That's really interesting. This kind of makes me wonder. So, sentence needs to live longer than the thing that it's inside. The let excerpt as the top is taking ownership, right? Right here is not doing anything, because all we're doing is saying like, hey, we're going to have a variable named excerpt, but it's not being set at all. It waits until here to figure out what type it's even going to be. There shouldn't be a big difference here. Let excerpt equals important excerpt, and then part this first part. And then immediately afterwards, we use it, and then they go out of scope. So when we come here, and we have our let excerpt, and we just use let excerpt, like actually then set its value right here. The only difference from what I can see is that this one lives longer than the sentence, and this one lives shorter than the sentence. So maybe the appropriate thing to say would be the lifetime of excerpt is longer than the content of excerpt, the sentence that goes inside of it. And that's a problem, right? Because this lives for more lines of code. The compiler is not sure that not sure that this that excerpt will still be that sentence will still be around for the same time that excerpt is, because literally they look at it and say, well, excerpt has this many lines, sentence has this many lines. So this is my new hypothesis for the lifetimes, which is it's just a count of the number of lines. And we can tell it, we can give it an override. It's not really an I guess we can't say an override. We can give it reassurance in some cases. But in other cases like this, it will just say, nope, I'm not going to do it. I don't trust you. It dies beforehand. Because if I put this back and hit save, we immediately get a lifetime problem again. And in this case, it doesn't even tell me that I can use a lifetime to keep it around. Instead, it says, note, values in a scope are dropped in the opposite order they are created. And that's the problem. So this isn't lifetime error anymore, although it's kind of like claiming that the borrowed value doesn't live long enough. What the real problem is that as it's undoing this, at the end of this block, it has an order that it's going to remove everything from memory. Okay, and it does it in the order in the opposite order in which these are created. So let me think about this. So we create if we think about this, we create string 1. So string 1 gets created. Then we create string 2. Then we create result. Then we end this block. So result gets removed, string 2 gets removed, but in this order. So result gets removed first, then string 2 gets removed. Of course, it's like not even milliseconds, like microseconds between each other, but Rust is not going to allow anything that might be able to come in and read that memory location. It's almost like we have to unwind the stack in our head. Yes, I think that's exactly what it is. So then we move on and we create excerpt. Then we create sentence. Then we create first part. Then we assign excerpt, but it doesn't like get moved down here. It stays in here in the stack. Then we use excerpt, and then we unwind. First part gets removed, and first part was just holding a reference, so that's not really a big deal. But then sentence gets removed, and first part was holding a reference to a point in memory in sentence. That point in memory was assigned to excerpt. Excerpt was pointing towards sentence, or like where sentence was. Sentence has been unloaded from memory, so excerpt is now pointing to some place that doesn't exist. That's why it doesn't work. Then this gets removed. String 1 exists, and we're fine again because nobody cares about string 1 right now. This is the reason why I can't like try to pull it in like into a parent scope and have that work. I would need to do this. Let sentence create that up here. Now we can have this. Then this should work. Because now we're saying like, hey, add sentence to the stack. We really need it in this order right here in this scope. Then add excerpt after this. So I can just do this way where I'm explicitly saying, hey, make sure that sentence is added to the stack in this location. That's really interesting. And it's sort of like something I hadn't really thought of before, and I'm sure will be very helpful because I'll be able to come in and when I get errors like it's not living long enough, I might be able to look at to see like, well, am I just doing things in the wrong order? And by doing this, I tell Rust, hey, I want you to put this in the stack before the other one. That's actually really interesting. So this works again. Of course, we don't have the lifetimes. It won't matter. You're enjoying this stream. You feed off my learning style and it's helping me understand. Well, thank you, Stacking. I'm glad that it's helpful to you. If I remove the lifetimes, again, it won't work, but that's because of this is a reference. And we need a lifetime specifier if it's a reference at all. So that is super, super interesting. I like that. I'm going to keep this in here so we can like come and remember what this is. I'm going to put in comment. We need to declare a sentence here because otherwise it would be moved from memory before excerpt. Things are removed in opposite order that they are created. A stack. Okay, so hopefully that will, if I come back here and take a look at this, it will remind me of like, hey, this is how to do that. That was a fun aside. Okay, so this struct has one field, part, that holds a string slice, which is a reference. As with generic data types, we declare the name of the generic lifetime parameter inside angle brackets after the name of the struct, so we can use the lifetime parameter in a body of the struct definition. This annotation means an instance of important excerpt cannot outlive the reference it holds in its part field. The main function here creates an instance of the important excerpt struct that holds a reference to the first sentence of the string owned by the variable novel. The data in novel exists before the important excerpt instance is created. In addition, novel doesn't go out of scope until after the important excerpt goes out of scope, so the reference in the important excerpt instance is valid. The other thing that I'm wondering about is like, is the lifetimes here become a runtime thing, or is it still a compile thing, but we're just telling it to double check? Like, yeah, those things, like if I could find somebody and like, I don't know, interview them or something, I would just love to ask them about lifetimes and have them explain things. The main function here creates an instance of the important excerpt struct that wait, I already did that one. Lifetime elision. You've learned that every reference has a lifetime and that you need to specify lifetime parameters for functions or structs that use references. However, in chapter 4, we had a function in the string slices section that is shown again in listing 1026 that compiled without lifetime annotations. That's why I was wondering what a lifetime is deep down in a machine code, if it was just a copy. Yeah, that's a good question. I wonder, maybe that would be a fun thing to do, which would be compile it to assembly and then inspect the assembly and try to see what's going on, and like do one where we give ownership and do one where we give where we do lifetime with a reference. I'd be interested in looking at that. I haven't done assembly in a really long time though, so it'll be interesting. Function, first word, we take an S that's a string reference and return a reference. Let bytes equals S as bytes. For I an item and bytes iterate enumerate. If item is the byte of string, return the string slice of S. Return that. The reason this function compiles without lifetime annotations is historical. In early versions, pre 1.0 of Rust, this code wouldn't have compiled because every reference needed an explicit lifetime. At that time, the function signature would have been written like this. So first word, lifetime of A. Yeah, so like the same lifetime of A. I think the Rust Playground lets you spit out the LLVM IR code. Ooh, interesting. After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotations repeatedly in particular situations. These situations were predictable and followed a few deterministic patterns. The developers programmed these patterns into the compiler's code so the borrow checker can infer the lifetimes in these situations and not need explicit annotations. This piece of Rust history is relevant because it's possible that more deterministic patterns will emerge and be added for the compiler. In the future, even fewer lifetime annotations might be required. The patterns programmed into Rust analysis of references are called the lifetime elision rules. These aren't rules for programmers to follow, they're a set of particular cases that the compiler will consider, and if your code fits these cases, you don't need to write the lifetimes explicitly. Yes, it allows you to do LLVM, IR code, and ASM, so maybe that would be a fun later. Yeah, definitely. I think we can write that down maybe. The elision rules don't provide full inference. If Rust deterministically applies the rules, but there is still ambiguity as to what lifetimes the references have, the compiler won't guess what the lifetime of the remaining references should be. In this case, instead of guessing, the compiler will give you an error that you can resolve by adding the lifetime annotations that specify how the references relate to each other. Lifetimes on function or method parameters are called input lifetimes, and lifetimes on return values are called output lifetimes. The compiler uses 3 rules to figure out what lifetimes references have when there aren't explicit annotations. The first rule applies to input lifetimes, and the second and third rules apply to output lifetimes. If the compiler gets to the end of 3 rules and there are still references for which it can't figure out lifetimes, the compiler will stop with an error. Okay, so the compiler uses 3 rules to figure out what lifetime references have when there aren't explicit annotations. So input lifetimes, the second and third rules apply to output lifetimes. The first rule is that each parameter that is a reference gets its own lifetime parameter. So that's like the A and B. In other words, a function with one parameter gets one lifetime parameter. So foo A. A function with 2 parameters gets 2 separate lifetime parameters. So A and B. And 3 and 4 and so on. We actually tried this and we couldn't figure out how to get that to work. The second rule is if there is exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. So yeah, if there's only one, we assign that to the output. The third rule is if there are multiple input lifetime parameters, but one of them is self or mute self, because this is a method, the lifetime of self is assigned to all output lifetime parameters. This third rule makes methods much nicer to read because newer symbols are necessary. Let's pretend we're the compiler. We'll apply these rules to figure out what the lifetimes of the references in a signature of the first word function in listing 1026 are. The signature starts without any lifetimes associated with the references. So function first word, taking a string that's a reference to a string, and return a reference to a string. So it's going to put a lifetime here of A. This is going to get A, and this is going to get A. When the compiler applies the first rule, which specifies that each parameter gets its own lifetime, we'll call it A as usual. So now the signature is first word, and we're initializing the lifetime parameter A, and then assigning it to the first parameter to the function signature. Battery running though. Uh-oh, hold on, need to fix that. Okay, that would have been bad. I plugged in the power source, but I didn't actually plug the power source into the notebook that's doing the actual streaming. So we would have just been happily going along until the thing shuts itself down. But we stopped that, so that's good. The second rule applies because there is exactly one input lifetime. The second rule specifies that the lifetime of the one input parameter gets assigned to the output lifetime. So the signature is now this. So now we add this output lifetime to the stir. Now all the references in this function signatures have lifetimes, and the compiler can continue its analysis without needing the programmer to annotate the lifetimes in this function signature. Let's look at another example, this time using the longest function that had no lifetime parameters when we started working with it in listing 1021. So we have longest, it takes in x, which is a stir, and y, which is a stir. And we return a stir. Let's apply the first rule. Each parameter gets its own lifetime. This time we have 2 parameters instead of 1, so we have 2 lifetimes. A goes to the first one, B goes to the second one. You can see that the second rule does not apply because there is more than one input lifetime. The third rule doesn't apply either because longest is a function rather than a method, so none of the parameters are self. After working through all 3 rules, we still haven't figured out what the return type's lifetime is. This is why we got an error trying to compile the code in listing 1021. The compiler worked through the lifetime elision rules, but still couldn't figure out all the lifetimes of the references in the signature. Because the third rule really only applies in method signatures, we'll look at lifetimes in that context next to see why the third rule means we don't have to annotate lifetimes in method signatures very often. So what we did to make this fix was that we just said, well, we're not going to have this be two different lifetimes. But we're going to say, hey, these both are going to be a lifetime. So we're telling the compiler, hey, as long as they both live at least as long as like the output, as the return value, then we're fine. Lifetime annotations and method definitions. When we implement methods on a struct with lifetimes, we use the same syntax as that of generic type parameters shown in listing 10.11. Where we declare and use the lifetime parameters depends on whether they're related to the struct fields or the method parameters and return values. Lifetime names for struct fields always need to be declared after the implements keyword and then used after the struct's name, because those lifetimes are part of the struct's type. In method signatures inside the implements block, references might be tied to the lifetime of references in the struct's fields, or they might be independent. In addition, the lifetime elision rules often make it so that lifetime annotations aren't necessary in method signatures. Let's look at some examples using the struct named important excerpt that we defined in listing 10.25. First, we'll use a method named level whose only parameter is a reference to self and whose return value is an i32, which is not a reference to anything. So implements, it initializes a lifetime of a, important excerpt, lifetime reference of a in here, our function level self, and this doesn't have to use any lifetimes at all. The lifetime parameter declaration after implements and use after the type name is required, but we're not required to annotate the lifetime of the reference to self because of the first elision rule, because we just don't have to do that in to self. Here's an example where the third lifetime elision rule applies. Oh, right, because we're not returning a reference, so we don't need to set the lifetimes here. So implement important excerpt, we initialize lifetime a, and we're using lifetime a in important excerpt. Function announce and return part. We take in a reference to self, and then we also take in announcement, which is a reference to a string, and we're going to return a reference to string. We're going to print line, attention please, and then the announcement. And we're going to return the self.part. Right, which is that part that we had in the structure. There are two input lifetimes, so Rust applies the first lifetime elision rule and gives both self and announcements their own lifetimes, which would be A and B. Then because one of the parameters is self, the return type gets the lifetime of self, and all lifetimes have been accounted for. Because we're returning self.part, which is on of self, and it ignores this one, then we're fine. I bet there would be a problem if we were to put both, if either of these could be returned. I kind of want to try that. So this would be important announce and return part. So in our struct, we can have a implement important excerpt. I'm not putting lifetimes in right now because I want to have it actually give us the error. Missing lifetime specifier. So immediately we need to use it because we have lifetime specifiers here, I believe. Okay, so we're gonna have our function, which is return part. We'll do it announce and return part. We're gonna take in a reference to self, and maybe we're gonna take in a reference to a oh, right, I don't have to give the type in here either, do I? But this one I do. I have to say that this is going to be my announcement, which is a reference to a stir. And I'm going to return a reference to a string. And so the way they've written it is, okay, we're first going to just print line, hey, this is the announcement. And we're going to put in announcement. They misspelled it. And then we're going to return self.part. But this is yelling at us, we need lifetime specifiers. So we could put this right here, have lifetime of A, and then we need to put it right here too. But at this point in time, it's now just yelling at us that we're not using it. So let's go down and use this. Excerpt.part. We can also maybe do print line excerpt dot announce and return part. This function takes one parameter, but 0 parameters were supplied. So we'll then pass in the stir, which is hello world. And there's no errors anywhere, so we could run this. Argo run. And this is, hey, this is an announcement, hello world. My guess is that we can cause a lifetime error in here by returning either the announcement or the self.part. So we can say something like, if announcement.length is greater than 5, then we're going to return the announcement. Otherwise, else, we're going to return this part. And this should cause, in my mind, like this should cause a lifetime error. Lifetime mismatch, but data from announcement is returned here. So yes, exactly. So now we have this parameter and a return type are declared with different lifetimes. Now we need to say the exact same thing we did before, which is, can I do this? I guess I can't use B anymore. Now I'm going to have to do B. Self B B B. Expected one of identifier or lifetime. Oh, it gave. Yes. So that's how we get it to work. So sort of like, I'm not sure I understand lifetimes yet fully, but I think I can use them, which is, okay, it wasn't sure which one of these, and it needs the return to be the same lifetime that these ones are, it assigns different lifetimes to each of these. But because it does that, it won't work. So I need to tell it like, hey, I have information here. Couldn't this still have a lifetime of A or B? I'm telling it to only have, I'm overriding what it would normally do and telling it has a lifetime of B. It's B. And it won't even then try to auto assign it the A or B. It will just do it on its own. Like it will just take what I told it to, because I'm the developer and clearly I'm the smartest one in the room, right? I mean, the compiler isn't better than me. I sort of feel that that's what I'm saying when I'm overriding what the compiler wants to do. But then this works. It may be a terrible idea, but it works. What happens to the A that we just passed? Is it just dropped? That I don't understand. Why we need this A here. If I switch this to B, or like just something else like this, would that work? Yes, it does. So this right here has no relation to here, this. It just needs a lifetime. And it has no relation to this either. It's just, yeah. I don't know. I think more questions. More questions about lifetimes, because why does this work? Or why does it not matter? And the book doesn't really explain this. It just says, you need that. The lifetime declaration and influence and use after type name is required. That's it. It's required. All right, we got 3 minutes left, but I'm gonna. Oh, we're so close to the end. I'm just going to get through this last little section, as long as we don't need code on it, and then I'll pack up for the day and get on with the actual work stuff. One would assume that all the A's would have a relationship. I know, that's how I feel. I kind of like, if I'm going to use lifetimes, I'm kind of thinking that I'm going to want to make them all very different from each other throughout the code, so that doesn't confuse me or anybody else. Because that's odd. At least in my mind, it's odd. The static lifetime. One special lifetime we need to discuss is static, which denotes the entire duration of the program. All string literals have the static lifetime, which we can annotate as follows. Let s sort of this reference to static stir. I have a static lifetime. The text of this string is stored directly in the binary of your program, which is always available. Therefore, the lifetime of all string literals is static. Wait, is that true in functions too? You might see suggestions to use the static lifetime in error messages, but before specifying static as the lifetime for a reference, think about whether the reference you have actually lives the entire lifetime of your program or not. You might consider whether you want it to live that long, even if it could. Most of the time, the problem results from attempting to create a dangling reference or a mismatch of the available lifetimes. In such cases, the solution is fixing those problems, not specifying the static lifetime. So it actually just stores that entire string. So it doesn't like put it in memory necessarily, it's actually on the disk. Generic type parameters treat bounds and lifetimes together. Let's briefly look at the syntax of specifying generic type parameters, treat bounds, and lifetimes all in one function. So use standard format display, function longest with an announcement. So we have a lifetime reference A and also a type. So it's a generic. So X takes in a reference to a reference to a string. Y is a reference to a string, and the announcement is an unknown type, so it's going to go through there. They're going to return a reference to a string, and then we're also limiting the type to where it has the trait display, which is why we bring this in. Then in a block of the function, do print line, announcement, and the announcement straight out. Then we say, okay, if x is greater than y, we'll return x, otherwise we return y. So basically it's the same thing we did, except we added a generic, so it creates multiple of these functions. As long as those types would have a display, that's all they're built for. This is the longest function from listing 1022 that returns the longer of two string slices, but now it has an extra parameter named an of the generic type t, which can be filled in by any type that implements the display trait as specified by the where clause. This extra parameter will be printed before the function compares the lengths of the string slices, which is why the display trait bound is necessary. Because lifetimes are a type of generic, the declarations of the lifetime parameter a and the generic type parameter t go in the same list inside the angle brackets after the function. So kind of overloading this, it feels like. Summary. We covered a lot in this chapter. Now that you know about generic type parameters, traits and trait bounds, and generic lifetime parameters, you're ready to write code without repetition, yet works in many different situations. Generic type parameters let you apply the code to different types. Traits and trait bounds ensure that even though the types are generic, they'll have the behavior the code needs. You learned how to use lifetime annotations to ensure that this flexible code won't have any dangling references. And all this analysis happens at compile time, which doesn't affect runtime performance. Believe it or not, there is much more to learn on the topics we discussed in this chapter. Really, I am not surprised to learn at all. Chapter 17 discusses trait objects, which are another way to use traits. Chapter 19 covers more complex scenarios, including lifetime annotations, as well as some advanced type system features. But in the next chapter, you'll learn how to write tests in Rust so you can make sure your code is working the way it should. I tried to write tests before, and that failed horrifically. So I am actually looking forward to that. So let's move on. We'll go to testing. So it's these write automated tests, and let's update where we're at. So updating the README. We're now in chapter 11. Okay, what happened? That feels odd. It just put these on different lines. Okay. Just programming languages. Okay, I just need this. My copy paste grabbed something weird. And we'll put the link in there. Perfect. Okay, so we have that in there. Let's also push up our code. We have our README and the main RS. So finished playing with lifetimes and updated where we are at. Go ahead and push that up. So I have a link to the GitHub where this code is in the stream description or in the YouTube video that this will be created. I can also put this into the Twitch stream chat here in case anybody wants to go and take a look at that. I'm going to be pushing this on up to YouTube. I'm a little bit behind in adding these videos to the playlist, so hopefully I'll be getting to that shortly, and then they'll be in the order. It'll be easier to find. They're up there. They just need to be added to the playlist. With that, thank you for stopping by and watching as I sort of fumble through and learn the lifetimes. It's actually really an interesting concept, but it's also really sort of difficult to understand. But it's also really fun to be able to play with this because I haven't seen this in other languages before. It's fairly unique. With that, I am generally streaming these every single morning at 7 a.m. Mountain Time. I forgot to tweet out this morning that I was on because I wasn't really sure if I was going to be able to stream today. If you would like a notification when you go live, follow me here on Twitch. Otherwise, you could also follow me on YouTube for when I do put those, when I do upload those, and when I put those in the playlist. Also, you could just follow me on Twitter when I remember Slack out or tweet out that I am going live or that I've uploaded some videos. With that, I am going to get ready for the day, go to work, and do normal day things. So thank you very much for stopping by again, and I hope that you have a great rest of your day. I'll see you tomorrow morning.